Good morning students. The next topic is permutation under the concept of fundamental principles of counting. So let us see the definition of permutation. Permutation is nothing but is an ordering of list of objects. So it is nothing but it is a arrangement. The meaning of permutation is nothing but the arrangement. So let us take an example of three different particular persons arranging in a bench. For example, let that objects be A, B, C or X, Y, Z. We don't know who are those. So let us take it A, B, C as a three people who are sitting in a bench, and I need these three people to be arranged. So one way I can arrange these in the same way, A, B, C. After that I can keep A as it is, and I can arrange in A, C, B, and then I'll keep B first. I'll place B in a first location, then I can arrange A and C. Then again B first, I can arrange in the format B, C, A. Then I'll keep C in the first position of the bench. Then it can be C, A, B. Then C again in the first. So B. So if I try to do the arrangements of these three objects or these three people, I can arrange totally in 6 ways. Okay, so this arrangement is nothing but the permutation. So permutation is nothing but an arrangement or ordering of a set of objects is an arrangement, or ordering of a list of objects is nothing but the permutation. So same example I have given here. For example, arranging 4 people, it's 3 people. Arranging 3 people in a line is equivalent to finding permutation of the 3 objects. So here I have, instead of 4, I have just taken 3. So is an equivalent to a permutation of the 3 objects. More abstractly, each of the following is a permutations of the letter A, B, C. So here if I have same thing I have written A, B, C, A, C, B, B, A, C, B, C, A, C, A, B and C, B, A. These are the ways where I can arrange the number of people. So it's nothing but is an ordering of list of objects. You're making them to arrange and you're giving particular position. In how many ways these 3 letters can be arranged is nothing but the permutation. So let us see the formulas for the permutation, different formulas or the different arrangements of the permutation. So let us see the first one. The first one is nothing but number of permutations of n distinct objects taken r at a time. So the formula is NPR is equal to n factorial divided by n minus r factorial. Okay, so this is the formula, major formula for the permutation, first basic formula. So here if I want to arrange n distinct objects, for example, let us take a previous example, that is A, B, C. We had A, C, B is a one possible. I took A as it is. That means one person I kept in the first. I arranged remaining 2, and I kept second person constant. I arranged third remaining 2. Again B, C, A, and then I had C, A, B. Then I had C, B, A. So these were the 6, right? So over here, number of permutation of n distinct objects. So how many distinct is there? 3 distinct objects taken r at a time. Here I told just arranging these 3. So r is also how many arrangements? How many arrangements you are doing? 3 arrangements. So it is nothing but 3p3. So if you see 3p3, if you put in formula, it is nothing but 3 factorial divided by 3 minus 3 whole factorial. So that is nothing but 3 factorial divided by 0 factorial. So you know 0 factorial is 1. So it is nothing but 3 factorial. So whenever you have NPN, that is 3p3, NPN, the formula is n factorial. NPN is equal to n factorial. Okay, so this is one formula, NPN, you can remember n factorial. Here, number of permutation of n distinct objects, like if they are told number of permutation of A, B, C, then you can do it in this. If they are told number of permutation of ABC taking 2 at a time, for example, if they are told number of permutation of n distinct objects of ABC taking 2 at a time, that means you are arranging only 2. So if it is so, you can put it in the formula as taking 2 at a time, 3p2. 3p2 means only out of this ABC you are arranging only 2. So it will be 3 factorial divided by 3 minus 2 factorial. So it is again 3 factorial divided by 3 minus factorial is 3 factorial by 1 factorial. So it is again 3 factorial itself, because in case if you get like this, then that is also 3 factorial divided by 3 minus 2 is nothing but 3 factorial itself. If you are taking 2 at a time, that means also it is also same, right? A, B, B, A. If you want to try this for A, B, C, taking 2 at a time, it is A, B, B, A. Then you have B, C, C, B. Then you have A, C, C, A. So this is the possible. So for that, again, one more formula is NP, N minus 1 is also N factorial. So this is the second formula. In case if you had a word WORD word, out of this you are taking 2 at a time. That means how many are there? 4 letters, that is 4P2. For this formula, if you put 4 factorial divided by 4 minus 2 is 2 factorial. So that is 4 into 3 into 2 factorial divided by 2 factorial. So there are 12 ways of arranging these letter word while taking 2 at a time. So this is the basic formula which you will be seeing the number of permutation, arranging and distinct objects taking R at a time. The second formula is different kinds of objects. So I'll just give an example of objects, different kinds of objects. So I'll just give the formula, that is nothing but n factorial divided by n1 factorial into n2 factorial into nk factorial. This formula can be used. For example, I'll give an example. You want to find the arrangement of the word Canara. Okay, you want to find the arrangement of the word Canara. Different kinds of objects, meaning is distinct kinds of objects permutation. So here whenever it comes in when they ask find the number of permutations of the word Canara or anything like difficult, there are few examples under this. You try to find how many times C is repeated. C is repeated once, A is repeated thrice, that is C is N1, this is N2. N2 how many times it appears? 3. N3 is N, it is appearing 1. N4 is R is appearing 1. So just put N, how many are there? 1, 2, 3, 4, 5, 6. N is 6. So formula you can apply here. 6 factorial divided by Canara is C is 1 factorial, A is repeated 3 factorial, N is repeated 1 factorial into 1 factorial. So this is the formula when you want to use different kinds of objects. So this is regarding this formula also we are using. Next, when you want to do arranging n objects, that means just arranging n objects. So same formula, arranging n objects, they are not given any at a time. So it is NPN, arranging n objects, you can write here. Arranging n objects. So you can take NPN factorial, so that is nothing but n factorial. Arranging n objects is n factorial. Next, arranging objects in a circle. Next, whenever you find arranging objects in a circle, then just see this, arranging objects in a circle, you can arrange it either in a clockwise. For example, there are 4 people, okay, there are 4 people, arranging them in circle. This is a circle, you imagine. Okay, there are 4 people and I want to arrange them in a circle. So if you take clockwise again this way, to take anti-clockwise it is this way. Let us consider clockwise, arranging 4 persons. Then what I'll do is I'll fix this particular 1 person over here itself. Remaining I should arrange. So how many are remaining? Now if there are 4 persons, remaining I should arrange, how many remaining? 3. So 3 factorial ways I can arrange this, because this person is fixed. Let me fix 1 person over here. Then remaining how many people are there? 3 people. Those 3 can be arranged in any of these positions, right? So it is nothing but 3p3. That is nothing but 3 factorial. So if I want to make it as a formula, I'll fix n as, if there are n persons, then arranging objects in a circle is nothing but n minus 1 factorial. There are n minus 1 factorial ways to arrange n distinct objects in a circle. See here, 4 persons are there. 1 person I'll fix it over there. Remaining 3 can be arranged in 3 factorial ways. So these are the 4 formulas which you should know before solving the problem. This is the required formula NPR when you take R at a time, or if you don't take also it will be NPN itself when you just do the number of permutation, that is this arranging n objects. When you want different kinds of objects, especially this formula we are using when it comes to the word kind of formula, n factorial divided by repetition of those letters individually, and then arranging objects in a circle we have n minus 1 factorial. Let us see the example problems. So example 1, in how many ways can n person be seated at a round table if arrangements are considered the same when one can be obtained from the other by rotation? So same formula what we had written here, that itself is given in the question, that's it. Okay, so if I tell in this problem, I'll tell what I can do is let one of them be seated anywhere in the circle. Let one of them be seated anywhere in this circle, anywhere in this circle. Okay, then the remaining, if one person of n is occupied, remaining is how many? Then the remaining n minus 1, then the remaining n minus 1 persons can be seated in n minus 1 whole factorial ways, n minus 1 whole factorial ways. So this is the total number of ways of arranging n persons in a circle. So same formula I told, for example, n persons needs to be seated in the circle. If one person occupies that place, remaining how many ways I can do the arrangement? So it is n minus 1 factorial ways. So in how many ways can n persons be arranged if they ask in a round table? Fix one person, one location, then remaining you should do the arrangement. So it is n minus 1 factorial ways. So this is regarding the example 1. Example 2, it is required to seat 5 men and 4 women in a row so that the women occupy the even places. So how many men are there? Total how many persons are there? Total there are 9 persons. Out of that 5 are men and 4 are women. Okay, it is required to seat all these 5 men and 4 women in a row. Condition is given that these women occupy only even places, only even place. So this has to be happen simultaneously. So obviously 1 2 3 4 5 6 7 8 9. Okay, so in the second position, fourth position, sixth position and eighth position, these are the even position. So in these even positions 4 women can occupy, 4 women can occupy. If you see over here, 4 women can occupy in 4 places. In how many ways? Considering they are sitting in even place itself, then it is 4 factorial. Remaining places are obviously odd, so 5 men can be seated in 5 odd places. In how many ways? 5 factorial. For example, if you had one woman, only one woman, then she can sit in this even places in how many ways? 4 ways. So we have 4 women over here. So obviously 4 women can occupy 4 factorial even places, like 4 places, right? So it is 4 factorial places. 5 men, they are 5 places are there. So they can be occupied in 5 factorial ways. See, formula if you use 4 women is there, they have to be seated in 4 places. So obviously it is 4p4, nothing but 4 factorial ways. 5 men is there, position you see 1 2 3 4 5. 5 men needs to be seated in 5 places. So that is also 5 factorial ways, because you apply the formula 5p5 is nothing but 5 factorial. That's what shortcut it is there, directly telling that 4 factorial ways and 5 factorial ways. Actually we are applying the formula itself, that is 5p5 and 4p4. But since they are happening simultaneously, we should apply the product rule. What is the product rule? It is required to seat 5 men and. If you remember the product rule, it is and 5 men and 4 women. So the answer is nothing but 5 factorial into 4 factorial. So this is the answer for this particular problem. So this was the explanation. So let us write in the theoretical answer way. So the answer is the 5 men may be seated in odd places. The 5 men may be seated in odd places in 5 factorial ways. and the 4 women may be seated in even places in 4 factorial ways. I hope no confusion in 5 factorial and 4 factorial. Just see here, 4 women, 4 even places. So 4 women, how can be seated in 4 even places? 4p4. 5 men and 5 places, so 5p4. Simultaneously it is happening, all should be seated in 9 places. Since it is and, we are applying the product rule. Okay, so the 5 men may be seated in odd places since women occupies the even places, and the 4 women may be seated in even places in 4 factorial ways. So therefore the total number of arrangements, therefore the total number of arrangements is 5 factorial into 4 factorial, that is equal to 120 into 24, that is 2880. This is the answer. So this is the required answer. This was just explanation to understand the concepts. The 5 men may be seated in odd places in 5 factorial ways. If not 5 factorial, you can write as 5p5 also, meaning is 5 factorial itself, and 4 women may be seated in even places in 4 factorial ways. Therefore, the total number of arrangements is nothing but the 5 factorial into 4 factorial, that is 120 into 24 is equal to 2880. So this is regarding the example 2. Let us go to the example 3. In how many ways can 6 men and 6 women be seated in a row? 6 men and 6 women. So again product rule is there. Please be conscious. 6 men and 6 women. So whenever this is happening simultaneously. So totally how many seats I want to occupy? 12. I'll just write here 6 men and 6 women, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 5, 6, 7, 8, 9, 10, 11, 12. Okay, in how many ways can 6 men and 6 women be seated in a row? Given a condition that if any person may sit next to any other, if any person anywhere, how many ways we can arrange that? Any person may sit next to any other. First question. There is no criteria, just I want to arrange these 12, that means total 12 people are there. Under that 6 men and 6 women, any person can be seated in any ways, anywhere. So it is nothing but 12p12, that is nothing but 12 factorial ways. So if any person may sit next to any other means it is 12 factorial ways. 12 factorial ways. It cannot be 6 factorial into 6 factorial. Because there is no condition, any person may sit next to any other. It did not tell that one should occupy odd place only, one should occupy even place only. Second one, if men and women must occupy alternate seat. For example, if here it is men, here it is women, here it is men, here it is women, here it is men, here it is women. Alternate place, men, women, men, women, men, women, men, women, men, women, men, women, men, women. Now you see, men can be arranged in 1, 3, 5, 7, 9. So totally it is 1, 2, 3, 4, 5, 6. 6 factorial ways. One men's can be arranged alternate, right? So either you can take it in odd places. Men can be seated in odd places in 6 factorial ways, and women can be seated in even places in 6 factorial ways. If men and women must occupy alternate seat, it is this condition is when men occupies odd place, men odd and women even. But there might be a possible that women can sit in odd and men can sit in even also. Okay, women can sit in odd and men can sit in even also. See here, if men and women must occupy alternate seats, they do not mention whether it is odd and even. So we need to find both the cases. So men odd, women even, we got 6 factorial into 6 factorial. When women odd and men even also, we'll get it as 6 factorial into 6 factorial. Finally, add these 2 factorial. So that is the result of this result. So this is regarding the example 3. So I'll write the statement for this. First problem, if any person sits next to another. Okay, so just write, if any any person sit next to any other, no distinction need to be made between men and women. Meaning is what? Next to another means there is no distinction to be made, no distinctions need to be made between men and women. I wrote in short M and W, you need to write men and women in their seating. So since there are 12 persons in all total, accordingly since there are 12 persons in total in all, the number of ways we can arrange is, the number of ways they can be seated, the number of ways they can be seated is 12 factorial ways. So you should find the value of 12 factorial. The answer is nothing but 479,001,600. So this is regarding the first example 3, first problem. If men and women must occupy alternate seat, you can write when men and women are to occupy alternate seats, the 6 men be, I'll write over here, second one, when men and women are to occupy alternate seats, the 6 men can be seated in 6 factorial ways in all. The 6 men can be seated in 6 factorial ways in odd places, and the 6 women can be seated in 6 factorial ways in even. Okay, so 6 men can be seated in 6 factorial ways in odd places, and 6 women can be seated in 6 factorial places in even. So therefore the possibility is, therefore it is nothing but 6 factorial into 6 factorial. So 6 factorial into 6 factorial is nothing but 720 into 720. 720 into 720, that is 518400. Similarly you write when the 6 men can be seated 6 factorial in even places, write it in that way, and the 6 women seated in 6 factorial in odd places. So therefore we'll get it as 6 factorial into 6 factorial again. So it is 720 into 720. So that is equal to 518400. Accordingly the total, therefore accordingly the total number of ways is 518400 plus 518400. So that is equal to 1036800. So this is the required answer for the example 3. So this is the required answer for the example 3. Just write the statement over here. Okay, I've just written this 6 factorial into 6 factorial. You're supposed to write the statement over here. So that is regarding the example 3. Example 4. 4 different mathematic books from 5 different computer science books. That is, we have 4 different maths book, 5 different CS books, and 2 different control theory books are to be arranged in a shelf. Okay, 4 different maths, 5 different CS, and 2 different control theory. Totally how many books we have? 11 books, I guess. Yeah, 11 books are there. Are to be arranged in a shelf. In that condition, how many different arrangements are possible if the books in each particular subjects must all be together. That means what? 4 maths books should be together. After that, 5 CS books should be together. These should be together. These should be together. In between you cannot get CS books, and in between you cannot. And 2 CT books too should be together. The meaning is the books in each particular subject must all be together, means these 4 books, see, this can be arranged in a shelf in like this. Like for example, let us total consider books is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 positions. Imagine the shelf itself. Here 4 maths books. So 1, 2, 3, 4 maths books and 5 CS books itself. CS and CT. Meaning is this: the books in each particular must all be together, each particular subject. So maths is all together, CS is all together, CT is all together. So this maths books can be arranged in how many? Within this there can be an arrangement. They must be together. Within this there can be an arrangement. So 4 factorial ways. And this CS, within them they can have arrangement. That is 5 factorial ways. And this CT, within them they have to be arranged. That is 2 factorial ways. 2 factorial ways. CT within them. That means what? CT can be here, CT can be here. Possible ways is 2 factorial. CS is what? These 5 textbooks can be arranged within themselves 5 factorial ways. Maths also within themselves 4 factorial ways. So that condition they have not told, that like fixed it is. Like they told that how many different arrangements are possible. If the books in each particular must all be together, they must be together, but arrangements within themselves can be done. 4 factorial, 5 factorial and 2 factorial. Now, but still, here these are 3, right? These are 3. That means this CS can appear together. CS might appear first, maths can appear next, and then CT. So there are 3 different arrangements. So it is 3 factorial. Imagine these as ABC. So you had seen those ABCs could be arranged in 6 ways. Same way, you remember this as one set, this as one set, and this as one set. So this can be arranged in 6 different ways. That is nothing but 3 different ways. So it is 3 factorial ways. So this is regarding the books in each particular subject must all be together. For that you just write the statement over here. For A, the maths book, the mathematics books, the mathematic books can be arranged among themselves in 4 factorial ways. 4 factorial different ways. The CS books in 5 factorial ways, and the CT books, control theory books, in 2 factorial ways. And the 3 groups like maths, CS, CT. What is the condition? The books in each particular subject must all be together. This should be together, this should be together, this should be together. But these can be arranged like CT can come first, that CT section can come first, then CS, then M. So just take ABC and you try to arrange. So those can be arranged in the 3 groups. The 3 groups in 3 factorial ways. Therefore, the number of possible arrangement is 4 factorial into 5 factorial into 3 factorial, 2 factorial into 3 factorial. So that is equal to 24. 5 factorial is 120, 2 factorial is 2 and 3 factorial is 6. Answer is 3, 4, 5, 6, 0. So this is regarding the first section. The books in each particular subject must all be together. Only the mathematics books must be together. Second, they have told that again arrangement is how many books we had? 4 plus 5 plus 2, that was 11. But only mathematics books must be together. That means only these. Then these can be jumbled within that. So this is taken as one set. This is 5. I mean 1, 2, 3, 4, 5, and this is 6, 7. So it is 8 factorial, and then mathematics books themselves can be arranged in 4 factorial. So this is the required answer. If you want, I'll just illustrate in the example again. You have 11 places, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11 for textbook. Okay, so in this, let us imagine that 4 maths books. This is maths books, and this, right, 5, 6, 7, there are 5 CS books and CT. Condition is only the mathematics must be together. These can be anyhow, that means CS, after CS CT can come again, CS CT, or it's just CT CS CS, like it can be anyhow. So this maths books I can arrange in how many ways? 4 factorial. Remaining this can be arranged in how many ways? 1, 2, 3, 4, 5, 6, 7, plus this one we have to consider as one single, so it is 8 factorial. That means 1, 2, 3, 4, 5, 6, 7, and this is taken as one single block, so it is 8, and within this they can be arranged in 4 factorial ways. So it is 4 factorial into 8 factorial is the required result. So I'll just write the statement for the second section. Consider the 4 maths books as single box. Okay, consider the 4 maths books as a single block, as a single block, sorry, single book, single not block, single book. Then we have, if you take this as single book, then remaining 7 plus this as 8, so then we have 8 books which can be arranged, 8 books which can be arranged in 8 factorial ways. But maths books can be arranged in 4 factorial ways. But maths books can be arranged in 4 factorial ways. So hence the number of arrangements is 8 factorial into 4 factorial, so that is equal to 40320 into 24, so that is equal to 967680. So this is the answer for the second sub question. So this is regarding the example 4. Example 5. This, if you remember, it's regarding the number of permutation of the word flower of length 4 can be formed. That means how many are there here? 1, 2, 3, 4, 5, 6. Okay, out of this 6 you have to find the 4. So how many different strings of length 4 can be formed using the letters of the word flower? So the meaning is nothing but the given word has 6 letters. All are distinct. The required is a distinct arrangement itself. In case if it was repeated, then we had to use that formula. Now it is distinct, so we can just find the answer. So the answer is nothing but permutation of 6, 1, 2, 3, 4, 5, 6. There are 6 letters. How many different strings of length 4? So it is P64. Answer is nothing but 6 factorial by 6 minus 4 whole factorial. So that is equal to 6 factorial divided by 2 factorial. So the answer is 6 into 5 into 4 into 3 into 2 into 1 divided by 2. So this and this gets cancelled. Answer is 360. How many different strings of length 4? 4 can be formed using the letters of the flower. Since all the letters are distinct, okay, since all the letters here are distinct, the required number of string is the same as the number of permutations of these 6 letters chosen 4 at a time. So this is the answer. So you can just write that the different strings of length 4 can be formed using the letter of the word flower in P6, 4, that is equal to 6 factorial by 6 minus 4 whole factorial. This is the answer. So this is regarding the example 5. Example 6. Find the number of permutation of all the word letter success. So you see write the letter success. So you just see here repetition is there. So right here the given word how many how much n, what is the n? 1, 2, 3, 4, 5, 6, 7. So right over here, first the given word has seven letters, of which 3 are S, 2 are C, and 1 is E, 1 is U. Okay, therefore the required number of permutation, I've already told regarding the formula for this. When you want to find the distinct number of permutations of such letters, n factorial is nothing but total count of this letters. So it is in our case 7 divided by the letters, individual letters, how many times. So it is n1 factorial into n2 factorial into n3 factorial into so on till nk factorial. This formula I am going to use. So here we have that is equal to the required number of permutation is nothing but 7 factorial n1 is s, how many times it has repeated, 3, n1 is s, how many times s is there, 3 factorial, u is 1 factorial, c is 2 factorial into 2 factorial, and e is 1 factorial. So this is the required answer. The answer is nothing but 7 into 6 into 5 into 4 into 3 into 2 into 1 divided by this 3 factorial is nothing but 3 into 2. I'll not write 1 again. Okay, into 1 and again 1 into 2 into 1 again 1. So here this 2 and this 2 gets cancelled, and 3 2s is 6, right? 3 2s is 6. So I'll cancel this and this. So left out is 7 into 5 into 4 into 3. Answer is nothing but 420. So this is the answer regarding this example 6. Similar problem, how many 9-letter words can be formed by using the letters of the word difficult? 9-letter they have to check whether 9-letter is there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So n is equal to 9. How many D is there? D is 1, I is 1, I is 2 here, I is 2, F is 2, F is 2, so 5 letters is done. C is 1, and U is also 1. If you see here, we'll write in this way. C, U, L, T, all are repeated ones. So what will be therefore what is the number of permutations of this letter? So how many 9-letter words can be formed by using the letters of the word difficult? So what is therefore the number of permutations of the word difficult is nothing but n is 9 factorial divided by all these factorial. So it is 1 factorial into 2 factorial into 2 factorial. See here, F is repeated twice and I is repeated twice. Rest all are 1 each. So write all. For C it is 1 factorial, for U it is 1 factorial, for L it is 1 factorial, and for T it is 1 factorial. So this is the question. That is nothing but 90720 is the answer. So this is regarding the formula of that n factorial divided by n1 into n2. So in that you had these two problems. Even this I could do with that, but since there is no repetition, I am using NPR formula, and this was like how many different arrangements of the books can be done. And same way with 6 men and 6 women, and these example 2, example 3, example 4 were similar. Example 5 was using NPR formula, example 6 and example 7 was using different kinds of objects. So this is regarding permutation 1 section of problems. The second set of problems will be discussed in the second video.